Okay, so in the previous lecture, I guess we had talked about we had already talked about linear functionals, if I recall, and then in the previous lecture we had talked about finite dimensional spaces, and we gave some important characterizations of finite dimensional spaces. In fact, we came up with a very important conclusion that if we are given a topological vector space which is locally compact, then that space has to be finite dimensional. So it's sort of a checking criteria whether you have given a space which is finite dimensional or not. And we had also talked about the Hein-Bodel property for finite dimensional spaces. And so our usual procedure, as it should be, to talk about whether we can have uh, some notion of a distance in an arbitrary topological vector space. Okay. Now, more or less, you guys, if you are watching this lecture series, then you should be pretty much acquainted with the notion of a metric, right? Okay, or rather, more specifically, the notion of a metric space, right? So, what is the usual motivation behind studying metric spaces? So, it's you can think of it just as a generalization. To be very specific, in a very layman term, it can think of it just as a generalization of the absolute value function over the standard reals or the standard complex as well. But that's not as accurate as it should be to talk about metrics to be generalization of just the absolute function, but typically speaking, it's a generalization of the notion of distances, right? Of the notion of distances. Distances of vectors you might think about, or distances of simply points on a space. Now we know that whenever we study mathematics over sets, it sort of helps us to analyze things much better when we have the notion of the geometry of how the points work, right? For example, if we can visualize how the points are acting on the space, then it's much better to analyze the properties that space should have, right? And metric spaces some sort of helps us in analyzing in that way. Topological spaces can be induced from a metric space using the open balls which we can construct using the metric, right? But the other way around is not obvious, as we had discussed in, I guess, in some previous lecture, that provided a topological space, it's not mandatory that it has or the topology has been induced by a metric, by a predefined metric or to be defined a metric. That's not always necessary, because there are certain important properties of a metric space which a topological space may or may not have. For example, all metric spaces needs to be Hausdorff in nature, but there are topological spaces which are not Hausdorff in nature. For example, the co-countable topology. The co-countable topology is not Hausdorff in nature. Okay, so it's not obvious that given a topological space you can account for a metric defined on that space such that ultimately the balls with respect to that metric will induce the same topology. In a more technical term, we say that the topology is compatible with the metric, right? But there are obviously some topologies which are indeed compatible with the metric, and those topologies, for obvious reasons, are more useful uh, in some sense, right? So whenever we have a topology, it should always be necessary to examine whether there are some conditions which can be imposed or which can be checked in order to have an information of the fact that whether we can account for a metric on that topology such that they are compatible, and that will be the topic for this lecture, is the notion of metrization. So in a very simple term, what does metrization means? Metrization very specifically means that provided a topological space, let me just strictly be in a topological space for now, provided a topological space, let's say x tau, the process of constructing a metric. There is a notion of a distance on that set, a metric on X, say D, such that D and tau are compatible. That is, the open balls with respect to the metric D, they form a basis for the topology, right? The union of those balls will generalize or will generate the whole topology. Okay, that is the fact. Now, as I just said, this is not always possible, but we are concerned about the fact when it's possible. Okay, right. Yeah. Suppose now this is just an observation that if a topological vector space X, let's say with the topology tau, is metrizable, then what is something which we can specifically talk about at this point, right? Like we had studied in the previous lecture that sorry, we haven't studied it yet, but I am assuming you have some notion of what balls are with respect to a metric. So if I have a topological vector space X tau and which is metrizable, then using the metric I can easily construct all the local bases around the points. Then the local bases of some point capital X in some point X in capital X is just, so what I can do in simple terms, so let me talk about it in this way. So suppose this is my X, or rather let me not be strictly Euclidean. Suppose this is my X and here is a point small x. What I can specifically do is I can simply consider a ball like this with radius 1 over n. Okay, right? So this will give me an open neighborhood of X with radius 1 over n, and in fact it is more important due to the reason that 1 over n can be made arbitrarily small, right? And we always look for things being arbitrarily small while analyzing sets or analyzing spaces, right? It's just the open ball centered at X and radius 1 over n, right? Okay, so now we sort of give an important characterization, or rather some important set of properties related to metrization, but we are not going to prove it in this lecture. The proof will be kept for the next lecture because the proof is quite confusing at some points, so it requires a dedicated lecture to itself. But here we state the properties of it, and we will use these properties extensively in order to claim other properties. Okay, so the theorem is as follows: if X is a topological vector space with a countable local basis, this is important. Okay, so the local base is in terms of the topology and it's countable. There are countable number of elements in the local base, and we know that whenever we are talking about simply local base, we mean local base at the origin. So with a countable local base, then there exists a metric D on X such that wait a minute, my print tablet is again causing problems. Okay. Metric D on X such that the D and tau are compatible. Okay, so X, let me say X tau is a topological vector space, then D and tau are compatible. Number B, open balls centered at the origin are balanced. Number C, D is invariant. this is quite important. D is invariant under translations. By invariant we mean indeed it's invariant under translations. What do I mean by that? That if I have the metric dxy, then it is the same, the distance will still remain same if I if I translate x by some fixed vector z and y by the same vector z for all x y z. Okay, that is what it typically means for being invariant. And number D, and this is an additional property, requires an additional property as well. So let me just mark it with a star, that if x is locally convex, if x is locally convex, then all the open balls are convex as well. Fine. Okay. So we leave the proof for now, and we move on to the next section, which requires an extensive discussion under metrization, is the notion of sequences. But not just sequences, one of the most beautiful type of sequences, the Cauchy sequences. Okay, so let's straight away dive up into Cauchy sequences. Now we know in some sense that whenever we study metric spaces, the notion of sequences, they arise everywhere, almost everywhere. Okay, whenever we talk about continuity of functions, they are there. Whenever we talk about closures of set, they are there. And in some sense the topology is somewhat you can completely characterize the topology in terms of sequences in some sense or the other. Okay, that is not always the case for in topology. I mean, if you are given a simply a topological space, that is not always the case, right? Because there are some important properties which are not satisfied in case of a topology, which are done in case of a metric space. Okay, but since we are talking about here a metrizable topology, so it has a well defined metric on it which is compatible with the topology. It's essentially required to talk about the sequences which can be constructed inside this space, right? Yeah, 1 second. Yeah, fine. Okay. Right. Now the usual notion of sequences in a metric space, if a quick recall, let's say a quick recall. Okay, so yeah, so this is just a recall. Let xd be a metric space, let xd be a metric space, then a sequence xn in x is said to converge to some x in x if for all epsilon greater than 0 there exists some capital N in n such that whenever n and m are greater than equal to n, the distance between xn and x, sorry, I do not need m here, I just need n. So whenever n is greater than equal to n, the distance between xn and x, this is less than epsilon, or the distance between xn and x can be made arbitrarily small. That's the notion of being convergent in a metric space. Fine. Okay. What about Cauchy sequences? What about Cauchy sequences? Now the usual notion of a Cauchy sequence is that when you have a sequence which in which the elements eventually come arbitrarily close to each other, right? What do I mean by eventually? This is what is meant by eventually. That is a property that is not always happening for the sequences, but it happens eventually after some point, after reaching some part of the tail of the sequence. Okay, for example, if you have a bounded sequence, suppose you have a sequence which is bounded above, let's say, and the sequence is eventually monotonically increasing, then it will converge to its supremum. Okay, you do not require the whole sequence to be monotonically increasing. If it's monotonically increasing after some point, and after some point it's just monotonically increasing, then we are done. In case of a sequences, what we actually need are properties of the tail of the sequence and not necessarily the whole sequence. Okay, so that's why I often use the term eventual, and that will be used throughout. Okay, right. So this is the usual definition of convergence in a metric space, and Xn is said to be Cauchy. Xn is said to be Cauchy if for all epsilon greater than 0 there exists again some natural number such that whenever we choose 2 points which are greater than equal to this natural number, then they are arbitrarily close. That is, the points in the sequence become arbitrarily close eventually. Fine. Now if you have a convergent sequence in a metric space, then it's always Cauchy. Okay, so this implication is always there. Why is it so? Because in mere language, if it's convergent to some point x, then eventually every term will be close to that point, and then you can choose two different indices for these terms, so both these terms will be eventually close to each other as well. Okay, this is a very simple proof of it. You can do it on your own. Just choose the triangle inequality and there is nothing else. But the reverse implication is not true in general. If it's true, then we call this metric space to be a complete metric space. That is, if Cauchy sequences are convergent as well, then we say the metric space to be a complete metric space, and complete metric spaces are obviously very important as well. Fine. Okay. Now what do we mean by convergence in a topological space? So in a topological space, let me just say it as well. So Xn is said to converge to a point x in a topological space x tau if Xn is eventually in every neighborhood of x. Okay, that is, let me say, suppose this is the point x, and say this is the sequence coming. So after some point it will be in every neighborhood of x. Okay, so once it enters, suppose this part, it's always inside this neighborhood, and it's always inside every neighborhood of x, right? Some sort of that. Clear? Got it? Fine. When is it said to be Cauchy inside a topological space? Again, if two terms are arbitrarily close eventually. But two terms are arbitrarily close eventually, that means that the difference between those terms, or rather I shouldn't use the term difference, the distance between those terms should be in every neighborhood of the origin, right? If two terms become arbitrarily close, that means the difference that means the distance between them are very close to 0, some sort of things like that, right? Okay, one more terminology let me introduce for now is that whenever we talk about the convergence or Cauchiness of sequences in terms of a metric, we call it to be D property. That is, it is a D convergent or a D Cauchy sequence, sort of things like that. And whenever we have things in terms of simply in terms of the topology, we call it to be the tau property. That is, it is tau convergent or it's tau Cauchy. Okay, tau property. Fine. Clear? So Xn is said to be Cauchy if Xn minus Xm is eventually in every neighborhood of the origin. Now there is something to observe immediately, that is this operation xn minus xm, this operation, this needs to be well defined, right? And this is obviously not the case, it is obviously not always well defined. For it to be well defined, we need to have an additive group structure to be in general. So it's better to talk about Cauchiness whenever we talk about, whenever we try to talk about Cauchiness, it's necessary to have a closed, rather an additive group operation. Specifically, it is better if we have it to be abelian. So it's always necessary to talk about Cauchy sequences in terms of a topology when we have an underlying vector space. You can think it to be some motivation in order to study topological vector spaces. Okay, fine. In fact, this definition of Cauchiness can also be somewhat manipulated to say that xn minus xm is eventually in every local base of the origin, right? So let me just state it for completeness, that fix B to be a local base of x, then xn in x is Cauchy if for all elements coming from this local base there exists some natural number such that xn minus xm is contained in V for all n and m greater than equal to n. Okay, and again we will claim this to be tau Cauchy. Okay, but we will see that eventually these notions, the tau property and the d property, are equivalent whenever we have a compatible metric. Okay, but observe that if x tau is a topological vector space and D is a compatible metric, then, so we had just seen that it needs to be invariant, right? Whenever we have a metrizable topological space, the metric is invariant, or rather let me be precisely writing that, and D is a invariant compatible metric. Then we can write dxn xm as simply dxn minus xm and 0, right? Now this is obvious that the d balls centered at the origin are the local base for the topology. And what does this claim therefore? Therefore, that a sequence in X is tau Cauchy if and only if it's d Cauchy, right? And in fact, this has some more consequences which you can just observe immediately, that in fact if d1 d2 are two such metrics, that is invariant compatible metrics on x tau, where x tau is again a topological vector space, then they have the same Cauchy sequences, right? They have the same Cauchy sequences, because if you have a d1 Cauchy sequence, then it's necessarily a tau Cauchy sequence, and then if it's a tau Cauchy sequence, it's necessarily a d2 Cauchy sequence. So we have a d1 Cauchy sequence if and only if a d2 Cauchy sequence, right? And hence they will also have the same convergence sequences as well, and also d1 is complete if and only if D2 is so. Fine. Right. So typically speaking, once we get hold of one such metric which is invariant and compatible with tau, it's enough to work with that only. We do not need to search for any other metric, right? Any other such metric. That's precisely the notion of it. Okay. So now we will study some important properties. There was a problem regarding my laptop, so yeah, let's continue the discussion. Yeah. So now we will talk about some important properties regarding this metric formed by the metrization. The first thing being called the dilation principle. The dilation principle. Okay. So let's quickly start with the theorem of it. It says that suppose xd1 yd2 are metric spaces and xd1 is complete, then then if E is closed in X and f from E to Y is continuous, then sorry, let me have one more property, is continuous, and the distance of fx prime fx double prime is greater than equals to d1 of x prime x double prime for all x prime x double prime coming from E, then the image of E under F is closed. Okay. And the proof is merely very simple proof. So I need to just choose a point which comes from the closure of the image of E under F. I need to show that it's still inside F of E. Right. So let Y be coming from the closure of F of E. Then there exists a sequence xn in E such that f of xn converges to Y, right? This comes from the mere definition of taking closure points. Okay. But if it is convergent, so it's Cauchy, right? But that implies that f of xn is Cauchy, and specifically it needs to be Cauchy in Y. Now by the hypothesis that this distance of fx and fy must be greater than or equal to the distance of x and y. So by that hypothesis, so if distance of two distinct points are arbitrarily close in y, it needs to be arbitrary, or rather in f of E, then it needs to be arbitrarily close in E as well. Now by the hypothesis, then xn is Cauchy. Xn is Cauchy, but what we have is d1 is complete, right? We have d1 is complete. So since d1 is complete, so that implies xn must converge to some x in capital X, right? But again, E is closed and xn is a sequence from E, which implies x must be in E, right? Now since f is continuous, we know by the sequential property of continuity, how can I write fx? I can write fx as the limit of fxn's, but then limits of fxn's was just y, but this implies that y must be in f of E, and this completes the proof, right? The next property regarding these metrics are also very important to observe. Let me do it in the new page. Theorem: let Y be a subspace of a topological vector space X and Y is an F space. Y is an F space. Okay, what do I mean by a F space? We'll come to this. Okay, then Y is a closed subspace of X. Y is a closed subspace of X. So let's prove it. Proof. Okay, what do we mean by an F space? Let us just quick recall that a topological vector space X is called an F space if its topology tau is induced by a complete invariant metric T. So the topology we are going to work in this case for Y should be this tau itself. Yeah. So let's dive into the proof of it, and the proof is again very simple. So let D be this metric. Let D be the required metric. Required metric in the sense the metric compatible with the F space. Okay. Let the B1 over n be the collection of all elements from the ball centered at 0 and radius 1 over n. So these are the points which has distance 1 over n, less than 1 over n from the origin. Fine. Okay. Yeah. Now let un be a neighborhood of the origin in X such that Y intersection un is just this ball 1 over n. So we construct this neighborhood in this way. Okay. And recall when we were trying to prove the notions of separability, there we had proved that provided a neighborhood of the origin, we can always get hold of a symmetric neighborhood of the origin such that adding two of those neighborhoods is still contained in the in the prior neighborhood. Okay. So let Vn be a symmetric neighborhood of the origin in X such that Vn plus Vn is contained in un and Vn plus 1 is contained in Vn. Okay. Fine. So these are the things which we will be working with. Now let X be a point coming from the closure of Y. We need to show that obviously X is inside Y. Okay. How do I show that? Define En to be Y intersection X plus Vn. Okay. Obviously n comes from the natural numbers. Now if Y if say let's say Y1 is in En and let's say Y2 is also in En, then Y1 and Y2 are in Y, Y1 and Y2 are in X plus Vn, then Y1 minus Y2, okay, so this is Y2, Y1 minus Y2 is in Y and also in Vn plus Vn, but Vn plus Vn is contained in un and hence in B1 over n, right? Because B1 over n was so it's the intersection of Y and un. So Y1 minus Y2 is coming from Y and also coming from un, so it must be in B1 over n. Fine. Also you can easily observe that the diameter of En, that is the maximum, the supremum of all the distance of the points, distance between the points in En goes to 0, right? This is to be observed. Now since each En is non-empty and Y is complete, therefore the Y closures of En has exactly one point in common, right? Right. This comes in some sort from the nested interval theorems, okay, or the Cantor's intersection theorem. You might also think of it in that way. Fine. We have a sequence of balls with their diameter going to 0, and all of these balls are non-empty, and Y is complete. That is necessary for the Cantor's intersection theorem in an arbitrary metric space. Y is complete. So there is exactly one point in common, right? And let that point be say Y0. Okay. Fine. Fine. Now we need to define one more set, and that will complete our proof. Now let W be a neighborhood of the origin again, obviously in X. Then again define Fn to be Y intersection X plus W intersection Vn. Okay. Then by the same set of statements, then the Y closures of Fn again have a point in common, say YW, but Fn is contained in En, hence the Y0 must be equals to YW, right? Now since Fn is also contained in X plus W, this Y0 must be contained in X plus W closure. The closure talked about in X, and this happens for all W, but this implies that this Y0 must be equals to X. But this implies, now if Y0 must be equals to X, then this implies that X must be in Y, right? But then this implies that Y closure is contained in Y, right? Okay. Because we had assumed X to be the point coming from the closure of Y, and this necessarily means that Y closure equals to Y. Fine. So the last property which we are going to talk about in this lecture and end it there is this theorem. A, if D is translation invariant metric on a vector space X, then I can write dnx from origin is less than equals to n times the distance of X from origin, and this I can write for all X in capital X and for all N in capital N. Now the proof of it is basically very simple. You just need to verify this property. You can do it on your own, that dnx 0, this is less than equals to the sum of distances of the point dkx and k minus 1x, where k ranges from 1 to n, and you can easily observe that this is nothing but n times dx0. Thus try to use the triangle inequality, and this is very trivial. Fine. Okay. The next property is somewhat more non-trivial, which says that if xn is a sequence in a metrizable topological vector space X, and if xn goes to 0 as n goes to infinity, then there exists positive scalars yn such that yn goes to infinity and yn xn goes to 0. Okay. Now the proof of this is again not that difficult. We just need to go through each step. Okay. See, we are given this, that dxn, the distance of xn from origin, goes to 0, right? Therefore there exists an increasing sequence of positive integers, that is, as we move ahead in the tail of the sequence in terms of these positive integers, the distance gets arbitrarily smaller and smaller, right? So positive integers nk, such that as we exceed nk, the distance between xn and origin, this becomes less than k to the power minus 2. So we are doing the same, so this abides by the definition of the sequence, nothing else, right? Let us just choose the scalars gamma n to be 1 if n is less than n1, and let gamma n to be k if n is between nk and nk plus 1. Okay. Then this is very easy to observe that d gamma n xn from origin is nothing but d k xn from origin, which is less than equals to by a k times dxn from origin, but that is so it is less than k times k to the power minus 2, so it is less than k to the power minus 1. This implies gamma n xn goes to 0 as n tends to infinity, and gamma n in itself, you can easily observe that it goes to infinity. Here gamma n and xn goes to 0. So this is the required sequence. Okay. Yeah. So let's end this lecture here. In the next lecture, we will talk about the proof of the metrization. But nevertheless, if we don't come up with the proof of metrization in the next lecture, we will talk about boundedness in the next lecture. Okay. So meet you guys in the next lecture.